Welcome, everybody. Thank you so much for joining us on Science Time with Cliff. I'm your host with the most from the East Coast, aka Dr. J. Bundy, and I'm here with my most trusted colleague, Cliff Bohm. I'm very excited about these streams. We're sort of going to start from the ground up. We're going to be introducing you guys to sort of evolutionary theory, specifically using digital evolution, so digital organisms and sort of populations that evolve in a virtual environment. Due to the sort of delays we've had today, we don't have a ton of time. Cliff and I both need to get out of here in the next 40 minutes or so. But I think Cliff prepared a presentation for us. Hey, Lena, so glad to see you first. So without further ado, I'm going to let Cliff go ahead and get into it. Thank you so much. Lena's our mod. Of course, she's showing y'all. We like people to let us know when they're first, second, or third. And then also to use that hi command when they come in so that the bot can welcome you. So thank you so much, Lena. And Cliff, do you have a presentation to share with us?
I don't, but
Oh, you don't, but you still want to jump into it?
I'm making something up as we go. You can
All right.
stall for a minute, and then we'll be.
All right, yeah, that's perfect. So I'll let you guys know what's going on. Cliff, like I said, Cliff is a PhD student at Michigan State University, unbelievably gifted programmer. He actually wrote the digital evolution software that I'll be using a lot on this channel. I've been getting so much positive feedback on doing these sort of work streams and these science-related things that I thought this would be great. I'm gonna have to build a Markov brain and start to build these evolving systems myself. Why not stream my streams with my colleague where I'm actually learning and preparing to do all this. Also, a lot of y'all have been rocking with me throughout the last few days. We have been covering the entire January 6th committee hearings, and I really appreciate that. We'll be doing more of that today. We also have, we're going to be revising our Vita Ed video. So we're going to be working on digital evolution education video. Sorry, y'all, I just woke up. And so I'm really excited about that. And so we'll be doing that this week. And that's another reason why it's so great if you tune into this stream, because you'll be able to go to this one, sort of start at ground zero, and then hopefully pick up with whatever we happen to be doing. And there was one more thing I was going to say about this all that's super cool. It'll come back to me. But yeah, I'm just great to have this. Oh, I remember. I'm going to put all these Science Time with Cliffs and all of my digital evolution related stuff on a playlist for you guys. So that's why I encourage Cliff to say, hey, man, let's start from the beginning. We'll build up from there. That way, people who come in even later or, don't catch this stream, but catch us maybe down the road and we're doing stuff and we're deep in the weeds on a project, we'll be able to say, hey, we've got a playlist. You can go back to the playlist. The playlist will help you get started from the ground up and sort of catch up with us. So we're really hoping to do a lot of the remediation that you guys have been talking to us about. People reach out to me and they say, oh, Jay, my science education was crap, or I always wish I understood evolution better. So I'm really appreciating the opportunity to get more into that. So that's what we're out here doing. Lena said she can't wait to get into the science. Yeah, that's what we appreciate. Also, guys, I did hear back from Mark Reed. I feel bad about this weekend. Mark Reed was supposed to join us to review his Kent Hovind debate with us, and we ended up missing him. So look for Mark Reed to be popping up this week. Also, I'm interviewing Jason Torn on Sunday on Hot Program. There's just, y'all know what it is. I'm out here every day. It's always a lot going on. Yeah, I think it's pretty good.
All right.
I'll probably do 3 shows today. All right, Cliff, do you want to share your screen with us, or?
Sure. Yeah, I can fake it.
YouTube Punk is in the house.
right, so I'm just gonna pick up where we were talking.
Yeah, give them the quick and
On
dirty,
Wednesday,
so for the people who don't, for cut off.
yeah. So the idea is, there was a question of what's digital evolution, and Jay said, where we start, what's the starting point? And I said, well, the starting point is, we can imagine a population. All you need for evolution is you need some inheritable material, you need some way to mutate, and you need something that selects from the mutations. So there has to be some way that some of those mutations are going to increase your reproduction rate, and some are not.
Cliff, do you like this? I used to say things have to be. Cliff, I used to say things have to be different. Those differences have to be, heritable. You have to be more like your parents than average, and some things have to reproduce better than others.
Yeah, I mean, one way that I used to, sometimes there's a game worth playing in order for evolution to work. And what I mean is, it has to be the case that that the difference is that there's something in the environment that can generate fitness difference, right? If there's nothing in the environment that can make a fitness difference, there's no game worth playing. It doesn't matter. Everyone's the same. If that makes sense. So that's the sort. Without selection, everybody's going to be the same. You're not going to, you're not going to get any. You can't get evolution. But I don't know. I don't want to wax philosophical too much. Here's the 10,000-foot view. Here's a population. These little orange boxes. Sorry, I'm laggy here. So here's a population that's got 100 orange boxes, and we're working with a model where I'm going to say that darker colors are higher fitness and lighter colors are lower fitness. And we're going to work with the model where we have size. So every generation, some of these individuals are going to reproduce and they're going to make a new they're going to make a new population. And just a technical thing out of the way, we're talking about a well-mixed population. So the order of these individuals in this list doesn't matter. So if I just want to say, okay, let's advance to the next generation, just going to produce another. Here's the offspring population. Right now, if we go from here to here, this would indicate that there were no mutations. So there's a new generation with no mutations. If we go another generation though, and let's say that in this generation we get, come on, oh, you're going to be difficult for me. Generation, let's say we do get one of these colors changing. We'll just change this one. This guy, his color, it's a little bit darker. So, right, I've got a population size of 50 here. If we see one mutation occurring after 2 generations, we assume our mutation rate is about 1%. It takes about 100 offspring to generate one mutation. And it happens in this case that this mutation was beneficial. Let's see what happens. We'll go to the next generation. So when we go to the next generation, the first thing that happen is this one guy, because he's going to have an advantage. So he may produce, he's going to produce within the average number of offspring. So rather than producing on average 1 offspring, he may produce 3 offspring. And then these other guys, they're gonna produce, we're gonna get some offspring from these guys. They're gonna be the lion's share of the population.
Yes, this is great. This is great. Go ahead, Cliff.
On average, 1 offspring. So we'll put these guys in here. And now these last 2 spots, let's assume that we got 2 more mutations out of the population. So out of all these guys who weren't one guy, all these guys, when they reproduced, 2 of these guys actually got mutations. And let's say that one of those was a beneficial mutation. And we'll make it a different one if I can get this thing to work. And we'll see it went to this. Oh, that didn't work. There we go. We'll say it went to this purple color. And we'll see the other one, this actually got a deleterious mutation. So it went to this light yellow. So now what we've got is in this new population size 50, 4 generations in, what's going to happen on the next generation is these 3, since we know that this guy has a free because he produced 3 offspring in the next. So each of these is going to have the same fitness advantage. They're also going to produce. So we're going to end up in the next generation. We're going to end up not with 3 of these guys, but we're going to end up with 9 of these guys. So these 3 here. I'll copy them out.
Cliff, this is so good, man. Cliff, can you hear me?
Yep.
Okay, great. Yeah. Keep going. This is good. This is great, guys.
Like a laser. Now,
oh,
this blue guy here,
don't let me interrupt you. Go ahead.
He's also high fitness. So let's just say, for sake of simplicity, he's also going to have fitness 3, which we're going to get 3 of those. And then this poor little yellow guy here, he's got a lower fitness than the average in the population. And since there's only one of them, sadly, he doesn't reproduce. Very sad. So he's going to go extinct. We're not going to see him in the next. And then the rest of the population is going to be made up of these. Yeah, exactly. The rest of the population is going to be these, we call them the wild type because that's what originally. So now we've got a population after 5 generations. We're looking at a population where there's different beneficial mutations that showed up. We actually saw 3 mutations, 1 in generation 3. We got another 2 in generation 4. But this deleterious mutation died off, and these 2 mutations are multiplying. If we now go forward in time, each of these is going to grow. Let's say in the next generation we need new mutations, but these are going to continue to the wild type. And so with this growth rate of 3, which is pretty astronomical, we're going to see that it's going to, at this point, is more than half the population. So red's going to be more than half the population. And these, well, on the next generations, because there's 3 of them now, they're going to be 9 on the next generation. So we'll drop down 9 of these. What we see is that the wild type, these orange ones, they're going to extinct. Just won't exist. They can't compete. And what we're seeing here is something called the genetic sweep. A genetic sweep is when some beneficial mutation arrives, and it takes a certain amount of time for that beneficial mutation to become dominant in the population. So you can see, I'm not going to stop doing this copy paste, but you can see if we label these guys, we'll call this thing, we'll say that this is generation 0. Pop up that.
There you go.
There's generation 0. And then generation 1 and 2 and 3 and 4, and I think we've got 6 here. Yeah, there we go.
Yeah, you got 6.
So we see that, we've got here's generation 6. You can see on the are be extinct because we're gonna more than double. We're gonna double the purple. There just won't be any room. So there's a lot more going on, but basically that's it. The beneficial mutations increase, the deleterious mutations die. And I mean, that's the program in a computer. Let's say that the orange ones here are zeros. I just have a list of numbers. They're all zero. And reds, I say have a 1. Purples have a 1. And these yellows here have a -1. And then I just say, look, for each increase of your value by 1, or let's make it easier. Let's say reds are 3s and purples are 3s and yellows are -3s. All right. So these are going to have, the oranges have on average a reproductive rate of 1. So they just maintain. The yellows, they produce 1/3 of an offspring for everyone. So you'd have to have 3 yellows to expect 1 yellow.
Yes.
And
Yes.
the reds, they have 3. So for every 1 purple or red, you expect to get 3 more in the next generation. And that's basically fitness. That's what we mean by fitness, or a fitness advantage. It just means that you reproduce faster.
Yeah, and the thing I really like about this, couple things. Number one, folks, like I said, we can have evolution on a chalkboard. We've gone with a digital chalkboard today, and you see how simple it is. Two, it's a perfectly valid demonstration. Now you might say, "Oh, these are just blocks on a chalkboard," but that's a representation of an actual population of boxes on a chalkboard, right? And what Cliff is demonstrating for you, we can set a mutation rate. Well, we're just going to randomly go through and say some of them go +1 and some of them go -1. That's a perfectly valid system of mutation, folks. But there's no genes. But you didn't flip any T's to C's or G's to A's. Nobody cares.
No, we don't need that. We don't.
And then the other thing is
heritable material.
The color was heritable.
That's what matters.
The color was heritable, and that's what matters. And then on top of that, you can visually see the change from one population to the next. It's right out there. If we'd extended it out a couple of more, you'd see pretty much all those dark reds and purples. We go even further, you will not see any more of that orange wild type. Right. So now, guys, if I go and
let me show another.
Yeah, go for it.
Some stuff I was working yesterday, actually. So here I was saying that this was a population from a social population. But each horizontal line in this figure represents one generation. So we start all, and this has a much weaker selection strength. So this isn't going to, like, our growth rates aren't going to be crazy like they were in the example. But up here, this is generation 0, and they're all identical in generation 0. And we start to see a mutation show up. But in this case, you have to get a bunch of bad mutations before you can get a good mutation. And so what we see is initially the population by drift picks up some of these bad mutations, but they always die off. Like this right here. This is an area where there was one of these bad mutations, but it wasn't so bad that it killed them off. But over time, it gets purged, it gets cleaned up. But eventually, they managed to get across this valley. They managed to accumulate enough deleterious mutations that they found a new beneficial mutation. And we can see that pretty quickly it starts to spread. And again, each horizontal line is one generation. So as we're moving down, well, this expanding triangle, that's our population. The population with the beneficial mutation, the subpopulation with the beneficial mutation is growing relative to the entire population. And at some point, they find another one of these beneficial mutations. Here they find another one. Here they find another one. And so this is actually a very simple system. It's the genome is, again, it's just a single number, but now we put it through this deceptive landscape that has, it's not just increasing your number is better and decreasing it is worse. Now it's, there are a few steps down and a step up and a few steps down and a step up, but you get, you start seeing these complex patterns.
Pretty looking complex patterns, actually. Well, it's like Cliff's abstract modern art. Although Cliff, we hang out with evolutionaries who actually do see this stuff at art, and they're all into the. They don't even get our colleagues started. They will actually give you a lecture on how there is Darwinian art. Shut up, nerd. But go ahead, Cliff. Can you hear me? Oh yeah, he's good. He's good. Go ahead,
Well,
Cliff.
yeah, I mean, you asked, so when you go fully get into this stuff,
There it is. There it is. See,
so this is
this is what I
showing
was
more of that.
talking
But
about.
now
Go ahead.
these white lines are showing the actual lineages through time. So what this is showing is dominant lineages through time. Anywhere where you don't see a white line, these are areas where they weren't very long lived. But this is showing us, I mean, when you want to get into more complex ideas, but you get into the idea of a clade, and a clade is the idea that you may have a single species, but that species may start to differentiate genetically. But eventually, if you wait long enough, one of those clades beats out the other ones. And here we can see like this grouping right here. This was at time 0. And again, we're seeing horizontal lines. The color indicates the fitness. So as they get to be lighter color, they're higher fitness. But this clade right here, it diverges, but you can see like that all the tendrils end. So this is a clade that goes extinct. And that's, this is what speciation, this could have been a species if it survived, particularly if it differentiated. This system doesn't allow for enough differentiation to support species, but it does certainly support parallel clades. So that's all I got to say.
This is this is fantastic. And guys, Cliff is the master of this. Remember, he might not talk about it a lot, but he used to work in animation for major motion studios, and then he was a designer of games. So this is a big deal to me because you'll see me guys meeting with Rodrigo, who's a grad student in our lab. And one thing that Rodrigo and I are constantly frustrated about is that science is often ugly. Make ugly graphs and use ugly fonts and don't really pay attention to the aesthetic of how we present our work. And with Cliff, it's really great because honestly, most of his graphs, as you guys can see, just look like straight up artwork. They're actually really gorgeous. Go ahead, describe this one for us.
Oh, this is just more of the same. This is very weak selection. So you can see that the leading edges here, as we go into lighter colors, they're kind of going all over the place. So this is indicative of very weak selection. The yellow here has a fitness advantage over the screen, but it's such a small fitness advantage. It's probabilistically over time, yellow wins out. But if you look at any single local area, it's very hard to tell which is better. And I'm actually showing every organism. So these lines, the reason why this looks so digital is because we're seeing every single ancestor. So, if I go to right here,
I see.
The parent of this was right here, and the parent of this was right here, and the parent of this one was right here. The parent of this one was right here, and the parent of this was right here. And so we can trace, we can go to a single individual at any point, and we could trace back exactly where they came from. But I thought
thing,
you get this crazy, like, almost like circuitry, computer circuit kind of layout.
Yeah. I'm with it. I'm with it. I'm 100% into the aesthetic, and it's crazy that that's actually real data. But also our point, guys, is it's actually a more complex version of exactly what he showed you today, right? You're just seeing the change in the population over time, drawing the connections between the lineage and depicting the phylogeny and the line of descent here. So this is super stuff. What I was gonna do quickly, because we have about hang on.
We got 15
I
minutes.
just came in and it does this thing where for a second, where it does this weird thing. All right, so what I think I'm gonna do real quick is I'm gonna try sharing my screen real fast, see how that goes. And what I'll show you guys quickly is you see a very similar thing in Avita, which is you guys, we start with the default ancestor. We've talked a little bit about that. We'll talk more about it, but I can go ahead and execute this run. And as you can see, the population starts changing over time. In Avita Ed, we also mark the fitness with different colors. You can see the colder colors are at the lower end, the brighter colors are high, and you can see over time, you see those colors emerging. as those mutations are happening, higher fitness and lower fitness organisms begin to emerge. But you guys can see already it's moved significantly towards the warmer colors. Now, eventually, Avita will keep rescaling it so that actually, so it doesn't sort of run out of colors. But again, just wanted to show you that what Cliff showed you is kind of a linear representation of these things. But when we're working in Avita Ed, we'll be looking at the virtual Petri dish, and you'll see all of the population sort of on this grid, and then you'll see the grid changing over time. I just wanted to make that brief comparison there. Cliff, go ahead and talk to us.
The difference here is this is a 2D population structure. And what that means is that when organisms reproduce, sort of like I was showing you these 1D spatial populations, but in a 2D population, when an organism reproduces, rather than saying the offspring can sort of, go sort of left or right because it's these populations are linear. You can go north, south, east, or west, right? Or northwest,
right?
Right? You go in the local neighborhood, and if you and then there are going to be certain effects. The growth rates are going to be faster because you can travel faster. But essentially, it's the same thing. Now, if we can also change the distance when an offspring is produced, we can say you can only place an offspring in a neighboring cell, and then you get these very structured populations. But if you say when you produce an offspring, you can place it 5 cells away, or you can place it in a random cell, then you move towards more random spatial populations, and you're going to get different effects. And one of the things people study is how population structure, how the flow of genetic material in space during evolution affects evolutionary processes.
Yeah, that's great. And I know your work looks at a lot of that stuff. And the thing that's great is in real life, you probably very hard to set up a system where you have spatial structure and not spatial structure, so you can only isolate the evolutionary difference of the spatial structure. But just like most other things, we can do it quite straightforward in a computer, and we get very clean results. Cliff, can you also give us a quick and dirty on Markov brains and maybe a elevator pitch for MABE, just so that just to get us previewing our next episode on Wednesday?
Yeah. I'll just pull something up. So I would say about the work I do is a pure evolutionary theory, and that's working with stuff like we've been looking at right now. The other half of it, though, is interested in trying to understand evolution of cognition. And I want to be clear that I'm not talking about human cognition. I'm not talking about mice. I'm not even talking about ants. I'm talking about the cognitive processes that we are likely to see in like a chemical pathway, right? We're talking like single-celled organisms are complex compared to what I'm working on. So what the way you can think about this is, if I have some chemicals and I mix those chemicals, maybe they're going to create a reaction, or maybe they're going to have a reaction that's going to generate heat. And maybe that heat is going to increase the rate of the reaction. And so we could start to see some logic. We could see that these networks will basically implement logic. And that logic is like and or, and basic true false logic just in the physical material. And the idea, my idea at least, is that the basis of life is the fact that chemicals will act in predictable ways and that they can implement basic logic. And okay, at the beginning, it's kind of like, all right, well, these are very simple systems, but you can start to see how, as these systems get compounded, you'll start to get more complex logic. And so I'm kind of entering at the point of I want to solve a task I'm interested in the evolution of agents that can solve some basic task. Realize one I want to pull up.
Yes. Jason Torn is here. Jason Torn is somebody I had in mind, Cliff. Jason Torn is another university guy. He's at the University of Idaho in Moscow, where Nkrumah Grant just was. Excited Jason Torn is in the house. He's one of the people who has been really encouraging me to do more science stuff. He's also a programmer, Cliff. When I had him on yesterday, we were talking about counter-apologetics.
Okay.
He was sitting over there working on his R code, and he uses Rust as well.
Nice.
So, and Python.
Nice.
So yeah, excited, Cliff. We're gathering our folk. They're starting to find us. We got about eight or 9 minutes left. So go ahead.
I just wanted to address what Lena said, which was not only does logic predate humans, but I have yet to hear a response to this. People talk about information requires a mind, and information is just correlated data. If you have two sources of data and they're correlated, that's one of them provides. They both provide information about each other. It's called shared entropy. Shared entropy is the definition of information. So if there are two sources of data and they vary in the same way, they have shared entropy, and that means that they have information about each other. If a rock rolls down a hill, and while it's rolling down the hill, the rock leaves an impression in the dirt. The dirt tells you something about the shape of the rock. There's no minds involved. That's information. Is it useful information? No, nobody's using it, but it's information. So anyone who says you need a mind to get information, they're just wrong. Now, I could come along and see that depression in the dirt, and then I could walk down the hill and I could find the rock that fits into that depression, and then I could follow the path up the hill and figure out where that rock came from. Now I would be making use of the information. But that whole idea that logic exists before we're around, information exists before we're around, absolutely. So I wanted to show you these animations real quick. I think that this is a good sort of, this will be a good.
Yeah, absolutely. Go ahead, share your screen, and I'll add you. I'll unshare mine, actually.
You're just getting into my...
No worries. Cameron Bennett asked how much he missed, guys. This is just going to be a standalone episode. So, and plus Cliff and I both have meetings in about 5 minutes. So, hopefully you guys will have an easy time going back and rewatching it. And like I said, I'm going to make these all on their own playlist. That's something I'll need to do this week. I have to organize the channel's playlist anyway. Go ahead, Cliff. I don't want to ruin your time. Here you go. I'm adding you in now.
So
go ahead.
These are two tasks. This one on the left here, this is showing something called, this was a paper I didn't work on. This was before I got to MSU. Up here now. Idea called predator confusion. Why do
hang on a sec, Cliff. You're coming in and out.
Hers blocking behavior, and one of the arguments was that
Cliff. Hang on, Cliff. We can't hear you. Yeah. You're kind of kill your camera real quick. And then after that, I'd say just count. I always say a little bit of count to 10 or something. Yeah, you're still coming in and out. Can you turn off your camera? Either that or refresh the restream. That often does it a lot too. Just refresh whatever tab you've got. Guys, to give you the quick rundown while Cliff gets situated. What he was saying is there's a question about predator confusion and swarming behavior. So when animals are dealing with the predator, a lot of times they seem to be running all over the place, kind of unsystematically. And there's an evolutionary biologist. They want to test all the ideas and figure out what's going on there. Some people that were at MSU with us, particularly. I think Randall Alston's a Beacon guy. Aaron Hintz, Fred Dyer, maybe Nooster, and certainly Chris Adami. And so Cliff is saying that this is some stuff they did right before he showed up at MSU, which is correct because this is from 2013. Cliff, are you there? Yeah, I'm not sure. Guys, if we don't get Cliff, it's okay. This was just sort of to tease our next thing where we get more into Markov brains. So I may just have Cliff present this to us on Wednesday when he comes back. Because I know he's got a meeting in a couple minutes. Cliff, are you there? All right. Oh, I hear him typing. Cliff, we can hear you. I'm not sure.
Yeah,
if
I'm having all kinds of connections.
Okay, no worries. I told them you got a meeting in a couple. Do you want to just pick this up on Wednesday at 1? And actually, I don't know what changes you made, but on Saturday, I think you were in a different part of the house maybe or something, or try plugging in your connection because over the weekend your connection and sound was actually a lot better. So look, go ahead.
I think it just doesn't want me playing an animation.
Oh, okay.
So I'll have to figure that out for.
Yeah. We'll try to figure that out for next time. Also, you can
just send you this slideshow so you can.
I was about to say the same exact thing. You could just send it to me, and on Wednesday I'll demonstrate it and play it or whatever.
I'll do that.
That actually sounds like a great idea.
And then
all right, that sounds like a great.
I'm gonna hit play on this other one and see if it'll.
Yeah, why not? Give it a shot. If we'll see what it is. It'll serve as a useful test anyway. I'm curious.
Oh, there we go. All right. So if you guys are seeing playing the idea here.
No, we're not seeing it play. We're not even seeing it play. It's all right. We'll look into. We'll take care of it because it's frozen. Cliff, I don't want to make you late to your meeting. I always do that. And then I have a 2:00. So hang on a sec. I'll mute Cliff. All right, guys. Thank you guys. Did that work? No, it didn't work. All right, guys. Thank you guys so much for tuning in. I think maybe I have my window going behind the scenes here. Let me switch views. All right, guys. This was so awesome. I'm so glad Cliff and I got a chance to do this. We've been trying to do this. We will do this twice a week. Every Monday, every Wednesday at 1 p.m. It's our normal meeting time. You guys will be joining us. Next time, we're going to start talking about Markov brains, Avita Ed, and start talking about MABE. So we're going to go from from evolution on a chalkboard to digital evolution in our virtual populations, and introduce you guys to the tools we actually use for our experiments. Cliff had a 2:00 meeting, so he just dipped out. I've got a 2:00 meeting. I'm going to dip out. I will be back right after my meetings are done for the afternoon, and we will be doing that January 6th. I believe we are on day 4, so that will be coming up today on my stream. I'll also be gaming and doing some behind-the-scenes stuff. Later this week, I'll actually start playing drums on stream. I need to get back into preparing worship music for our weekend shows. The idea with late night Counter-Apologetics and stuff like that is that since we're an atheist church, I want to play drums for you guys, play a worship song, then start the show. So look forward to streams this week where I'll be playing drums. We'll be working on our Avita Ed video. Of course, you're rocking with the United States champion. We are off and running on a long week of a lot of work and a lot of broadcast. I hope you choose to join me. Like I said, I'll be back this afternoon for, I'm not sure exactly what time, but I'll be back for the next day's coverage of January 6th. I want to thank you guys all so much for tuning into this. I want to thank everybody for coming. Y'all already know what the deal is. Let's get into this chat right here. Let's drop these little buys in the stream chat. Myron Bottle, go ahead and let us know that we're all poofing. So go ahead and y'all, it's time to go ahead and drop that buy-in. Poof with me. I will see you all later. I greatly appreciate you all. In the name of the Darwin, the Dawkins, and the Christopher Hitchens, science bless you all. Why? Because figuring stuff out is better than making stuff up. I love you all. I'll see you in a little bit.